Okay, then we actually need to complete the remaining parts for the deflections. Last one we mentioned about the virtual work method, and then we left a method we call the Castigliano method. For the Castigliano method, actually it is similar to the virtual work method and then also energy method. And then here is the description for the Castigliano theorem. The Castigliano second theorem states that the displacement of a point is equal to the first derivative of the string energy in the structure with respect to a force acting at the point and in the direction of the displacement. That means we differentiate or partial differentiate the string energy. Then it becomes the deflection of a force. And then for slope at the point, actually it is equal to the first derivative or first partial derivative of the string energy of the structure with respect to a moment. So here you can see that this is the proof for that. Well, again, sorry about that. There is some question mark here. Actually, they are the bracket. Maybe I show the PDF instead. Then they won't have the question mark right there. Okay, sorry. Chapter 6. So for here, you can see that actually it is equal to delta I is equal to du dpi. That means the differential partial derivative of the string energy with respect to the force pi, then it is actually equal to delta I. Now don't worry too much about the derivation, but right now we would like to apply this equation to find for the deflection. Now for a truss here, if you still remember, for the string energy, Ui, is actually equal to the force, and then half, and then times the deflection. The deflection is NL over EA. So you can see that the string is actually half, and then N square L over EA. And then you need to add all the member force together, so it is summation. So right here, this is the so-called the string energy. And then if you partial derivative with that, then actually just the N is a variable. So actually you will have the equation like this. So summation of N and then times dN dP times L over EA. Now comparing to the so-called the virtual work method, if you still remember, it is N L over EA. So this one is actually similar to this one. And then you can see that N is still N here, L is L here, and then you have AE here. So the small n actually is replaced by dN dP. So right here, you can immediately find that actually the two equations are very similar. And I will show you how to use this Castigliano method and then to find for the deflection of the truss. So we will use this, we call it Castigliano method. Castigliano is the name of an engineer. So he invented this method. So you can see that this is a truss. And then we want to determine the vertical displacement, the joint C of the truss. And then the cross-sectional area of each member is 400 mm square, and E is equal to 200 gigapascal. Now, to use the Castigliano method, we also need to add a force. For virtual force method or virtual work method, we add a force of 1 in the structure, okay? But for this one, we will add a force, which is an unknown. Usually, I will indicate it as a P. Now, if I want to find the force at the joint C, I will add a force at the C here. So I will add a force, and then it is called the P, okay? And then by using the equilibrium equation, actually all the member force will be in terms of P. So you can see that if I add a P here, then I can, from the equilibrium equation, you can see that they will have the P inside your equation. So for here, you can see that for the support reaction, the P will be here, and then the P will be here. And then if you find the equilibrium equation by considering different joints, say for example, you consider joint A, then you can see that your member force will be in terms of P. And then NAB will also be in terms of P. Your support reaction will be in terms of P. So you can see that all your member force will have P inside, okay? And if you still remember, if we want to find the delta, we have the summation, and then N is the real member force, and then we have dN dP, and then L over EA. So we need to find what is N, and then find dN dP, and then find the length, and then the Young's modulus times the area. So right here, you just have your equation. So we have N and then dN dP L over AE. N is actually the member force, as I mentioned before. So here is actually the member force. This is the member force. It is in terms of P. So you can see that AB is equal to 0.667 P plus 2. AC is equal to negative 0.833 times P minus 2.5. And then BC is equal to negative 0.833 times P plus 2.5. And then you can derive or take differentiation with respect to P. So this one is easy. If you take a look for differentiation, again, it is simple. If you differentiate if a constant, you just take it away. Okay? And then if you take a look, there's a P right there, you just cross out the P, then it becomes 0.667, 0.833, and then negative 0.833. So the integration again is easy. If it is a number, just take it away. And then if you see a P, because it differentiates with respect to P, you just cross the P out, then the number remaining will be dN dP. Okay? And if you still remember, this P originally is not there. There's not a P here. The P is artificially you add by yourself. Originally, there's no P at the structure. You add P by yourself, right? 之前冇啊，你自己特登加落去嘅啫嘛。So P actually is equal to 0, okay? So actually, you can find the values of N, because actually you can see that your equation here actually is N, and then you can find N, and then you put P is equal to 0. If you put P is equal to 0, then you can see that originally it is here, and then you put P equal to 0. You put this one equal to 0, 0, 0. Then it becomes 2, 2.5, and negative 2.5. Agree? And L is the length. So you have your n is equal to 2, and then you have dn dp is equal to 0.667, and then L is equal to 8. So this one is actually equals to 2, because n is equal to 2, times dn dp is equal to 0.667, and then times 8. Then you have 10.67. Okay? So this one again is quite straightforward. Then to here, this one again, it is equal to 2.5 times 5, and then times negative 0.833. Then you get a value of 10.42. You just multiply this one by this one by this one, and then this one, it becomes this one. Okay. So if you have this, then you just add them together. Then you have 10.67. So this is why you have 10.67 here. And then you divide by the values AE, then you can get 0.133 mm. Okay. So this method again is quite straightforward. So for here, you need to determine the horizontal displacement at the joint D. The truss here, the cross-sectional area of each member is indicated in the figure. So you can see that each of the member dimension is not the same. Some are 385 mm square, some are 577.5 mm square, some are 770 mm square. So for this one, if you want to find the horizontal displacement at the joint D, what do you need to do? As I mentioned, you should add a force P at the location where you want to find for the deflection. So for here, you will add at the point D here, and add a force P right there. Then you can find for the support reaction in terms of P and the member force in terms of P. So if you apply a force P there, then you can see that your support reaction are in terms of P. Then you can see that it is in terms of P, in terms of P, in terms of P, in terms of P. So you can state your N right here. All of them actually are in terms of P. Then you can have partial derivative of N with respect to P. Then the first three answers is equal to 0. And then dA is equal to 1.25, BD is equal to negative 0.75. And then you can see that the P originally is not there. There's no P. So you can put P is equal to 0. And then when P is equal to 0, the first one equal to negative 60, the second one also equal to negative 60, the third one equal to 75, and then the fourth one equal to 75, while the last one is equal to negative 90. So that's why you get this value. And then from the equation, you know that actually if you want to find the answer, you need to multiply N by dN dP by L. So you just multiply these three numbers together. But for here, you can see that each member have different cross-sectional area. So you have 468.75 divided by its own cross-sectional area and Young's modulus. And again, for the BD, you have the n dn dp times L is equal to 202.5, and then you will divide by its own E and A. Then after that, well, you just calculate the values together. It is equal to 7.84 mm. Okay. And then we have another example here. Determine the vertical displacement of the joint C of the truss. As shown here, assume that A is equal to 300 mm squared and E is equal to 200 gigapascal. Now for this one, actually, you can see that we want to find the displacement of the joint C. So just like before, we need to put a force P at the location C right here. So you can see that I still need to put a force at the C, which is actually equal to P, okay? So when I try to find for the answer, I need to put a force P at the location C. And then if I do it this way, then my truss becomes something like that. You can see that I have a force P at this location, okay? Then you may ask, hey, Simon, before it should be 20. If you put P right there, what will happen? But it doesn't matter. You just follow the procedure. Put P right there. And then you can see that your support reaction will be in terms of P. And then your member force will be in terms of P. And then this one in terms of P, this one in terms of P, this one in terms of P, etc. All the member forces are in terms of P. How can you do that? You just use method of join. Then you can find all the member force. And then you can find the P will be inside each of the member force. So if you put all the expression in this table, so you can see that for the first one, second one, third one, fourth one, and then up to the final one. All of them are in terms of P. Then you can take the partial derivative with respect to P. So as I mentioned, for constant, it is equal to 0. And then for P, you just take it away. So you have 0.33, 0.667, 0.667, etc. Don't forget, originally there's a force right here, which is equal to 20 kN. So when we try to find the member force, we will put back P is equal to 20 kN. So you put P is equal to 20 here. You put P is equal to 20 here, etc. Then you will find the values of N, like this. And then you have the length here, which is equal to 3 meter, 3 meter, 3 meter, etc. You put all the length here. And then just like before, you have your first term times the second term times the third term, then it is equal to your N, dN, dP, and then times L. And then you will add them together. And then you can get the values 369.7 kNm. And then you have this value just divided by AE. Then you can find for the deflection. Okay. So very similar to the virtual work method. Very, very similar. And then actually this method can be extended to the beam. For the beam, actually, it is quite similar before. So actually, as I mentioned before, you will have delta is equal to mm over EI and times dx. This is the virtual work method. And then in Castigliano method, you just replace this m by dm dp. And then if it is for rotation, instead of dp dm, I mean dm dp is dm d dash. dm dm dash. Okay? That means if you want to find for the deflection of a point, say for example, if you have a beam here, if you want to find, for example, you have a distributed load here. If you want to find for a deflection at this location, you add a force P here. Then you will find for the moment function. And if you want to find for the rotation of the beam, then instead of adding a point force P there, you will add a moment there. Say, for example, you have a beam here. And then if you want to find for the rotation, say, for example, you have a deflection like that, you want to find for the rotation at this point. Then instead of adding a force right there, you add a moment here. That means you will add a moment m dash right there, and then find the dm d dash. So I will show you in the example. For example, if you want to find the displacement of point B for this beam, what will you do? Then, as I mentioned before, you add a point P at the ends of the beam. So you add a point P here. And then find the moment in terms of P. So you can see that I'll add a force P right there. And then I will cut the free body diagram and then find the moment in terms of P. So you can see that I will take the moment at this location. And then you can see that for the first one is negative m. For the next one is negative 12x and then times the moment Rx over 2. And then the last one is P times x. Because they are in clockwise, so it is a negative value. From here, you can see that your moment is equal to negative 612x squared. Negative 6x squared should be. Minus px, okay? So you will put p that is equal to 0. Because p is really equal to 0, then m is equal to negative 6x squared. For here, if you have the p, then dm dp is equal to negative x. So you have your moment equation, and then you have your dm dp. So you just substitute dm dp here. And then you have your moment here. This is your moment. And this is your dm dp. This is your moment. This is your dm dp. Then after the integration, you get 15 and then times 10 to the power 3. And then finally, you have 150 mm. Don't worry too much because this is your first time to know. And then I will have some more tutorial to you in the next lecture. So you will be more familiar with this very soon. And actually, we can also extend this value to the frame structure. For this one, we want to find the slope at the point C. So for this, actually, as I mentioned, we will add a moment m dash at the point C here. We add one moment there. And then we will express the moment equation in terms of the m dash. So for here, you can see that I can find the moment equation for the horizontal member and then for the inclined member. Then you can see that M1 is the equation for the horizontal member. And then you have dm1 dm dash is equal to -1. For the same way, actually, you can find for the inclined member. M2 is equal to -108 and then times x2 cosine 60 degree plus 1.8 minus m dash. This one actually you can get it by cutting the free body diagram. You can cut right here and then you can find for the expression. And then you can see that dm to dm dash is equal to -1. And then again, you just integrate for the horizontal member and then you have the inclined member respectively. So you can get the rotation, which is equal to 0.0255. I mean 0.0225, okay? Now you can take a look first. If you have a question, then of course you can ask anytime. Okay, and then we have a new chapter today. And actually it is about the statically indeterminate structures. So for here, we will mention about the analysis of statically indeterminate structures by the so-called force method. Now, actually, the force method is not very difficult. Actually, it is very basic. And the way why I need to introduce is that before we mentioned about the determinant structure. Determinant structures, that means actually our equilibrium equation is good enough to solve for all the unknown. But however, sometimes we will add more support reaction than we require for statically determinant structure. So that's why we need some new method to solve for the indeterminate structures. So here we will talk about statically indeterminate structures, and then we will talk about the force method for analysis, and then the Maxwell theorem for reciprocal displacement. We call it the Bette's law. And actually, the force method can be applied to beam, frames, truss, And then I have some additional remarks for this method. And then actually, I just give you a very simple example. Basically, you have a simply supported beam here. This one we call it the statically determinant structure. Okay. Now for this one, if I have a structure, I have a load on that, then you can see that the deflection is very large. Agree? Then if I add one more support here, what will happen? 加多個頂喺中間，我會點啊？ Then the deflection will be much smaller, right? And then the maximum stress will also be smaller. So actually, in this case, it becomes 1, 2, 3, 4. I have 4 unknown reactions. But at the same time, I just have 3 equilibrium equations. Now, what does that mean? That means I don't have enough equilibrium equations to solve for all the reactions. And then this one we call that indeterminate structure. Okay. For this one, because I have one more support than the determinant structures, so we call that the degree of indeterminacy. Is equal to 1. And then for this kind of support, we call it the redundant support. What does that mean, redundant? Redundant 即係多餘嘅。我原本唔加落去佢都穩陣㗎，幫我加咗個多餘嘅 support 俾佢，令到佢更加穩陣。We call it the redundant support. But as a structural engineer, we always want the structures to be indeterminate. I want to put more support in the structure to make it more stable and safe, right? So for the indeterminate structure, actually the member thickness can be thinner, and then the stability can be higher. So always we want to have the so-called the indeterminate structure. However, we don't have enough equation to solve for all the answer. Then actually we need some new method to solve for the support reaction. Because we just have 3 equilibrium equations, which is not enough. So for here, besides the equilibrium equations, we need one more. We call it the compatibility equation. It depends on the displacement requirement of the structure. Okay, so for here, actually, when we apply the so-called the force method, we use a very basic principle. We call that the superposition. Now you can see that for this beam, you have the first beam here. I mean the support reaction. You have the second support reaction here, and then you have your moment here. Then you have 3 support reactions, and then you have one more support reaction here, right? So we call that this one is the indeterminate structure to the first degree. Then by using the so-called the principle of superposition, you can see that, well, originally I have one structure here, and then I have my force here. This is my original structure, and then I have my support here. For so-called the superposition method, I can decompose the case into the 2. You can see that for the first primary structure here, I just take the By away. Take By away. Then if I take By away, there will be a deflection delta B here. The whole beam will go downward. But however, my By is here, so I need to add back my by here. So for the case 1 plus the case 2, it becomes my original structure, right? So if I apply the by, that means there will be a vertical diffraction here. I call that delta dash BB. But you can see that originally here is actually a support. So the diffraction must be equal to 0. So if I add them together, I assume that going downward is negative. So negative delta B, and then plus delta dash BB, because this one is going downward, the diffraction, this one is going upward. When they add together, it must be equal to 0. Because originally here is actually a support. There's no diffraction at this location. Do you agree? So this is a new equation that we just developed. We call that as a compatibility equation. Together with the equilibrium equations, then I have four equations. Then I can solve for 4 unknowns, right? So from here, you can see that my original beam here, and actually I can decompose it to the 3. I mean to these 2. The first beam and the second beam. And then, well, right here, I have a By. But instead of a By, if I have a force equal to 1 here, I will describe the diffraction as FBB, okay? Then if my force is By, then what is my diffraction? If my force is By, I just multiply this by the By. Then, of course, the diffraction also need to multiply with By as well, right? So the diffraction is equal to By times FBB. Okay? So this delta dash BB is actually equals to By times FBB. Then if I have this one, you can see that delta B dash over FBB is actually equal to By. So by knowing 2 diffractions, I can actually get the values of By. So this is actually the diffraction due to unit load. Sorry, this one should be delta B, not delta dash BB. This one is delta B. Delta B is actually the diffraction due to the real load. So you have delta B here, you can find it. And then FBB, you can also find it. How to find the diffraction? If you still remember, we can use 3 methods. We can use conjugate beam. We can use a virtual work method. Or we can use double integration method. That means what you have learned before for diffraction is very useful. And then you can use it to find for your redundant reactions. Okay? So if you find the diffraction here, and then you find the diffraction here, then you can find for the answer. So this one is very, very useful. And then for the reaction, actually you should still remember, for the beam, actually we need to take the redundant reaction away and then to find the deformation. Actually here you have the freedom to choose which one is the redundant reactions. Now before we treat By as a redundant reaction, and then right here you can see that you have a normal force at A, you have a shear force at A, and then you have a moment at A. And then here actually we can choose the moment at A is the redundant reaction. If that for the primary structure, we will take away the MA. If MA is being taken away, then you can see that there will be a rotation at A. And then, well, for superposition, we need to add back the moment. So for here, we will add back the moment here. If the moment is equal to 1, then the rotation, we call that the alpha AA. And then times the magnitude of the moment MA. So theta dash AA will be the final moment, final rotation. Then if you can see, it is a fixed end here. Then actually the overall rotation should be equal to 0. So theta A plus theta dash AA must be equal to 0. So you can see that theta A plus MA alpha AA must be equal to 0. So theta A, actually this one is known. You can use the so-called the virtual work method, or you can use conjugate beam to find for the rotation. And the alpha AA, again, this is known. And then with alpha AA is known and then theta A is known, then you can find for the MA. After find for one redundant support reaction, then you can use the equilibrium equation to find for the remaining answers. Well, the values we just used before is just one support reaction. That means just one redundant. But right here, you can see that we have an example. Actually, we have more than one redundant. You can see that at the A, we have two support reactions. And at B, at C, at D, we have one support reaction respectively. So for here, you can see that you have 5 support reactions. But you just have 3 equilibrium equations. That means it is an indeterminate structures with the indeterminacy equal to the second degree. Right? So for this one, again, if we can still use the force method for analysis. We can take away the support reaction at the B and then the C at the same time. So you can see that when we take away the support reaction at B and then at C, then actually there will be deflection at B and then at C, okay? And then you can see that we will add back the support reaction one by one, By and then at the Cy respectively. Then at the location here, you will see there is the delta dash BB and delta dash CB. Now for the first letter, actually it is the location of the deflection. And then the second letter actually means the loading location. So for here, you can see the FBB is actually the displacement at the B when the force is applied at the B. Well, here you can see that delta CB here. That means the location is the C, while the location of the force is at the B. So here we use delta dash CB. That means it is the location of the deflection is at the C, and then the loading is applied at the location B. Okay. So you can see that it is FCB and then times the BY. And then similarly, you can see that we will add back the support reaction CY here. And then due to the force CY, actually at the B, there will be a deflection. We call it the delta dash BC. Because it is actually the displacement at the location B due to a force at the C. So it is called delta dash BC here. And that is equal to CY times FBC. And then finally, we have delta dash CC here. Again, it is actually the deflection at the location C due to a force at the C. So it is equal to CY and then times FCC, okay? So you can see that by superposition, actually they can be equals to 0. Because originally there's a support here, there's also a support here. So you can see that you have a delta B, and then plus this delta dash BB, that means BY FBB, and then plus delta dash BC and then CY FBC here. Should be equal to 0, because here actually the deflection is equal to 0. Then again, you have delta C plus delta dash CB and then plus delta dash CC, then it should be equal to 0. For this deflection, actually they are known. They are known here. You can calculate them. You can calculate this one. 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 So all the deflection can be found by using previous chapters knowledge. Then right now you just have two unknowns, BY and the CY. So you have two equations, two unknown. So you can able to find the support reactions by solving these two simultaneous equations, okay? So actually this method can be applied to a very high number of indeterminacy. But however, you need to solve for n simultaneous equation for n unknowns for the support reactions. And then you can actually make this one to be a matrix. And then when the matrix becomes very large, actually it is very difficult for you to solve for the answer. So actually this is not the best method when you have high indeterminacy. And then in order to make your life easier, there is a so-called the Maxwell's theorem or reciprocal displacement or Betty's law. And then you can see that for this law, it means that FBA is actually equal to FAB. So that's why, well, physically means that it is the deflection at the B due to the loading at A is equal to the deflection at the A when the load is applied at the B. So for this reciprocal rule actually makes you have less burden. Because once you calculate FBA, that means you automatically you can find FAB. For here, I will just tell an example for beam. So for here, you can see that you have the force here, and then you have a force here, and then you have a moment here. And then you also have a support reaction in the B. Then for here, actually, first of all, you will choose the redundant reaction. Now, usually you will choose the force at the B. And then after you choose the force at the B, you will take the redundant force away. And then, well, due to this 50 kN, you can find for this delta B. And then due to this BY, you can find the values of FBB. FBB is actually that the load right here is equal to 1 kN. Then the corresponding displacement is equal to FBB. If the load is equal to By, then the deflection is equal to By times FBB. Then you will know that actually for equilibrium, negative delta B plus By FBB must be equal to 0. Well, in case you know the delta B and then the FBB, I'll give you some table. You will search for this value because it is too time consuming if you find the deflection by yourself. So for these questions or this type of question, I'll give you a deflection table and then you can check for that and then to find for the answer. And then for here, you have this deflection and then you have this deflection and then you can find By is equal to 15.6 kN. Okay. And then for here, again, we have a fixed end beam on both sides. Now, because actually the horizontal force can be ignored because the horizontal force must be equal to 0. Then here, actually, this beam becomes a degree of indeterminacy of second degree. So we will choose two support reactions to be considered. So right here, we will choose the moment for both as the fixed end support to be released. So you can see here, I will take away the redundant reactions of both sides. So I have a theta A and a theta B on the left-hand side and then on the right-hand side. So when I apply the load, I will find theta A and then I will find theta B. And then for one side, I will add back my support moment, and on the other side, I will also add back my moment. But as you can see here, my original both sides are the fixed support. So the moment, the rotation must be equal to 0. So theta A plus theta dash AA for theta dash AB must be equal to 0. And on the right-hand side, theta B plus theta dash BA plus theta dash BB must also be equal to 0. So you can see that I have two equations, and then I can find for the values of MA and MB. Now, this one are known because actually you can use virtual work method, cantilever method. It's virtual method, conjugate beam method, or double integration method to find for the deflection like this. And then you have two equations, two unknown. And then once you find all the rotation, then you can find for the moment. Sorry about that. The question mark are still the bracket. Then you can see that you have two equations and then two unknown. Then you can find for MA and MB. Okay. But actually, the method can be also applied to the frame. Say, for example, I have a frame like that. You can see that I have a support here, vertical support. I have a support here, and then support here. I can choose one reaction as the redundant. Here, I will choose the horizontal force here as the redundant. And then I will remove it. Then you can see that, well, when I remove it, there will be a deflection delta A right there. And then in order to use the so-called the method, I will add back the load, AX here. Then I will have a deflection AX FAA. Then you know that originally it is a pin support. So when this plus this, delta A plus AX FAA must be equal to 0. Now then the delta A actually can be found by using the virtual work method. FAA can be also found by using the virtual force method. Now I don't want to go into very detail. Now this one is the integration. Sorry about that. Sometimes it will have the wrong displays if it is something in Excel. So actually for here, we use the virtual work method to find for the diffraction, delta A. Here. So delta A, after using the so-called the virtual work method, I can find for this answer. Now again, you just use the real load and then the virtual force, and then find for the real moment and then the virtual moment. So you have mm over EI times dx and then integrate along the member. Okay. Now you can take a look first, but for here, I don't want to go into details because actually for the diffraction, I won't ask you to do like that because it is too time consuming. Okay. But you may take a look for reference for the values. And then again, you also need to find for the diffractions, which is actually FAA. FFA is that when AX is equal to 1, then the diffraction is equal to FAA. So for here, you can see that this is the reaction equal to 1. Again, this one is integration. Then you can find for the values of FAA. Again, they use the so-called the virtual work method here. And then you still use mm over EI and then times dx. For this one, again, I will give you the table to find for the diffractions. So this is just for your reference, how to find the diffractions by using the virtual work method. And then once you find the delta AA and FAA, then actually you can find for the support reaction AX. So this one is actually quite straightforward. But the most difficult thing is that to find for the diffractions only. But for the diffraction, don't worry too much. Actually, I will give you the table. I'll show you later, and then you can take a look how to use the table to find for the diffraction. And actually, the method can be extended to truss. Well, however, this one I will just give you as a extra material to take a look, because actually it is not common to apply this method for truss. But the idea is that again, you can find for the indeterminate truss, because right here the member actually have one more member forces than the number of equilibrium equations. So this is an indeterminate truss. And again, first of all, you will take away the redundant supports or redundant members. So you will take away the force inside this member, and then you will find for the diffractions. And then afterward, you will add back the force and then find for the diffractions. It's originally in the same member, so the diffraction is equal to 0. So you have delta AC plus FAC and then small FACAC. Then it must be equal to 0. You just use these compatibility equations then to find for the answer. Now for this one, actually, don't worry about that. It is not commonly used to use this method for truss. And then this is mainly for your reference. And then we just use the so-called the virtual work method to find for the diffractions for a truss. And then again, this is actually for the case when you have one, I mean the force inside the truss member. And then, as I mentioned, if you use 1 right there, then you will find for the FACAC. That means when this is 1, then the diffraction is equal to FACAC. But of course, the real force is actually equal to big FAC, so you need to multiply with this one. And And then from this, you can find for this support, the member force within the members. But so for this method in general, you can solve for any number of redundancy. If you have n number of redundancy, then you have n simultaneous equation to solve. But this method is not very useful when the number of degree of indeterminacy is too high. Okay. We will introduce you some other methods later when you have very high indeterminacy. Okay. Then this one I just introduce you about the way how we can solve for the answer. Okay. In the next lecture, I will have some tutorial questions for you and then to familiarize this method. Okay. But I think it is around 10 already, and then I will end the class now. Okay. Do you have any questions before I end the class? Okay, let me stop recording. 好啦，記住啦，嗰個測驗咧，我哋今次定咗19號，應該冇乜人有問題啦，係咪？咁咧我就應該係考到 conjugate beam 嗰課，應該係 chapter 5嘅啫。咁你哋就起碼温到 chapter 5啦，好嘛？咁呢課咧，下一個禮拜咧，我都有啲 tutorial，咁我哋到時大家一齊做啦嚇。第一次聽，可能係未掌握到嘅，但係呢個又唔係好難嘅啫。不過大家要識做啦。下次我哋揾埋啲題目一齊試下做啦，好嘛？好啦，咁冇問題，我哋到呢度啦。咁啊，辛苦各位啦。OK，拜拜。
拜拜，唔該阿 Sir。